Okay, so I'm going to take off where we left off in class yesterday on Tuesday the 15th of May. We did some problems finding the Laplace transforms of functions using the definition. And then we had theorem 7.11, which gives us the Laplace transforms of some basic functions that we'll see appearing. And in example 5, we showed that the Laplace transform was a linear transformation. And then example 6, what we did is we went ahead and applied the linearity and our transforms of basic functions. On the homework, you'll have some problems where you do Laplace transforms by definition. Other problems where you will use theorem 7.11 together with the fact that the Laplace transform is a linear transformation. Okay. And then I left off in class talking about what a piecewise continuous function was. That's a piecewise continuous function is one on which, on any closed interval, there's at most a finite number of discontinuities. And we talked about exponential order. The function f is said to be of exponential order c. There exists constants c, m, and t, capital T, such that the absolute value of f of t is bounded above by exponential function with ct in the exponent, and then that inequality just has to be true for all t greater than some capital T. So what this says is basically that in absolute value, the graph of f of t eventually is going to be outgrown by this function m e to the ct. Okay, so maybe at first f of t is larger than that function, but eventually at some value, capital T, the exponential will outgrow the function f of t. Now, I talked about theorem 7.1.2, the sufficient conditions for existence of the Laplace transform is that if f is a piecewise continuous function on 0 to infinity and of exponential order c, the Laplace transform exists for s greater than that value c. Okay, so that just means that for the Laplace transform to exist, that just means that that indefinite integral will converge. And that's true as long as s is greater than c. Now, I talked about maybe going through the proof here in this video that I would make. The proof is of this theorem as well as 7.1.3. The proof of these are in the textbook, so you can go ahead and read those if you like. So what I'll do is I'll do example 8. We'll find the Laplace transform of a piecewise function. And then theorem 7.1.3 just says if you're piecewise continuous and of exponential order, the Laplace transform will then exist. And then the limit as s goes to infinity of the Laplace transform will equal 0. And again, that proof is also in the textbook. So I think what I'll do is I'll skip the proofs. I'll let you read them if you're interested. But on this video, we'll just go through example 8, doing the Laplace transform of a piecewise function. Okay, so we'll find the Laplace transform of f of t, where f of t is the function -1 on the interval from 0 to 1, and then f of t would be +1 for any value of t greater than or equal to 1. Okay, so we start out Laplace transform of f of t. This is going to equal the integral from 0 to infinity. So by definition of e to the minus st times f of t dt. And then since the piecewise function is broken up at t equals +1, we can now split this up into two integrals. So we can do the integral from 0 to 1, e to the minus st, but on that interval from 0 to 1, f of t is going to be negative 1. And then we're going to do plus the integral from 1 to infinity of e to the minus st, and as long as t is greater than 1, f of t is equal to positive 1. Okay, so let's take care of that first integral. The first integral, well, the negative 1 can come out front, and the integral of e to the minus st is minus 1 over s times e to the negative st. So that would just be 1 over s e to the minus st, and then we'll have to plug in 1 and subtract what you get when you plug in 0. And then it's plus, and then I'll write this. It's going to be the limit as a goes to infinity of the integral from 1 to a. As a matter of fact, what I'm going to do is actually do the integration as well in this step. Okay, so now the integral of e to the minus st is minus 1 over s e to the minus st, and then we're going to do that from 1 to a. Now, for the first function, when you plug in 1, you get 1 over s e to the minus s, and when you plug in 0, you get 1 over s. The 1 over s can be factored out, and I'll just write this is e to the minus s plus 1. Okay. And actually, that's my bad, the sign in the middle, right? We're supposed to be subtracting. So this is e to the minus s minus 1. And then we're going to have plus the limit as a goes to infinity. I can plug in a and get minus 1 over s e to the minus sa. And when I subtract that negative, it becomes a positive, and you're going to get 1 over s e to the minus s. Okay. And then actually taking that limit on the right, so we still have 1 over s e to the minus s. I think I'll write it in this form, minus 1 over s. And then the limit over here, this first term, minus 1 over s e to the minus sa, is going to converge to 0 as a goes to infinity. If you want, just plot the graph and take a look. And then the second term is really a constant. So this would be plus, now let me switch back to black. So it would be plus, and then the limit of the first term is 0, and then the limit of the second term only involves s. It doesn't depend on a, so I'll pick up a 1 over s e to the minus s. And finally, the Laplace transform will then be, so we have 2 1 over s e to the minus s, so what you get is you get 2 over s e to the minus s, and then I'll get a minus 1 over s. That could be factored or simplified a little bit. Only thing I could really do is maybe factor out the 1 over s and rewrite the expression with no negative exponents, but that is the Laplace transform. So when you're doing a Laplace transform of a piecewise that's broken up at a particular value, you would just break up the integral at that value, and then one of the integrals will be a definite integral and the other one will be an improper integral, and you would do the integral from 1 to infinity, replace infinity with a and put a limit a goes to infinity out front. And then, like I said, the other two theorems, I will let everybody read the proofs in the textbook if you're interested. If a function's piecewise continuous and is of exponential order, the Laplace transform exists. And then the second theorem says that when the Laplace transform exists, it converges to 0 as s goes to infinity. Okay, this certainly agrees with, if you look at theorem 7.1.1 and you look at all these functions on here, I don't think it would be hard to convince yourself that all of these would go to 0 as s goes to infinity. Okay, so I'll wrap it up there. Keep the video short, 10 minutes. Thursday we're going to start section 7.2. We'll talk about inverse Laplace transforms, and then we'll actually start using Laplace transforms to solve some differential equations. Thanks for watching, and I'll see everybody on Thursday.